So there's a lot of stuff happening on board the International Space Station, a lot of different systems that work to support the crew members. And one of those systems actually just celebrated a birthday this week. I think it was 7 years running now. And that's the regenerative life support systems on board the International Space Station, a very integral part of just keeping the crew members safe, keeping them alive, keeping them empowered to do their duties. I'm joined now today by Dave Mathers, currently one of the managers in the ISS mission evaluation room, the ISS MER, and he used to be an OSO, so you were an operations support officer, correct?
Yes, it was.
All right. Well, pretty important birthday for the regenerative ECLIS, the life support system. That's pretty cool. And now you were an OSO. You used to work directly with that. What was your role back when you were an OSO to work with this stuff?
So the OSOs, they are structures, mechanisms, and maintenance.
Mm-hmm.
So not only the nuts and bolts that hold the space station together, but also fixing, repairing all the systems as they break down, or need to have the preventive maintenance as need be. So when I came out of college, I came into the OSO group and was assigned to the ECLIS system. Mm-hmm. And at that time, Regen ECLIS was still on the ground, still going through its final testing and things like that. And they were working to send it up early, and we were going to install it in the lab before Node 3 mm-hmm. got there, because Node 3 was going to be much later. So we had a lot of work to do to get the system up and get it installed in a place where it wasn't designed to have been installed in the first place. We had to modify the lab and install cables and hoses and mm-hmm. new panels and things
yep.
like that that weren't there before, and retrofit retrofitted a vent that goes to space so that we could vent the hydrogen eventually when it comes from the oxygen generator. So that was a lot of work, and the system was still on the ground, and so we hadn't developed any of the procedures for doing any of the maintenance once it got up onto space, right, onto the station. Mm-hmm. So being assigned to the ECLIS system and being a new guy, I was a little more expendable than the folks that were console. So I got sent out to Marshall a lot. I took a lot of trips out to Marshall Space Flight Center to do fit checks on the systems as they were being installed. And the OSOs do that a lot for mm-hmm. all of the hardware as they're flying. So I'd go and see if the tools fit, if there's anything different between what the engineering said it was going to look mm-hmm. like, and also, since the OSOs train the crew on maintenance, they have an insight as to how the crew is going to see things, so they can do those fit checks, understand what the crew is going to see, understand what we're going to need to put in the procedures, and so on. So I got to get very familiar with all of the regenerative life support systems and hardware, mm-hmm. Because I was going and actually seeing all the hardware and putting tools on the nuts yeah. and bolts and writing down notes and things like that.
Okay, well, I mean, since you got to live it, you got to breathe it, it sounds like, why don't you walk us through kind of the three major components of this regenerative life support system?
Sure. And briefly, there's actually kind of a fourth cousin component, okay. as it were, the waste and hygiene compartment. Mm-hmm. It has to come from there. So when the crew members,
it all starts somewhere.
It all starts somewhere. So they have to go to the bathroom like everybody else. So when they use the restroom, mm-hmm. That meets up with some pre-treat, which keeps bugs from growing and keeps crystals from forming, yep. so that later when we concentrate it at all, it doesn't clog up the system. It goes from there into the urine processor, which is in WRS, Water Recovery System Rack, mm-hmm. number 2. Goes into the urine processor, where there's some filters in there, but mostly just for catching fuzz, the lint and stuff that may have come out, or crystals, or some solids that may form. But mostly it's a distillery. So it's old technology being applied in a new way.
Okay.
So the distillation assembly is the heart of the urine processor, and it brings the pressure down. So we bring it down to near vacuum inside the distillation assembly, and it's just a spinning drum so that it keeps the fluids all on the outside. One of those low gravity adjustments we need to make. It does that, and we heat it up a little bit and evaporate the water out, and then so whatever's not water gets left behind, and that goes around a few times to make sure we mm-hmm. get all the water out. So you keep trickling in a little bit more from the waste and hygiene compartment, and as it goes, pulls the water out, and then that water goes into the water processor.
Okay.
Where it meets up with condensate, condensation that we pull from the air. So our common cabin air assemblies, the heat exchangers, the air conditioner, basically, for the space station. If you know your air conditioners at home, they condense, or in your car, they condense, right? The moisture in the air condenses on the cooler surface. So we draw that moisture out, and this is the moisture that we breathe out, or that we sweat out from our normal day-to-day activities.
This is just more stuff coming from the crew. I mean, they
other
don't
ways
even
that the crew
realize
gets
it,
rid of water.
They're putting more water back into the system.
Yep. And if we didn't take that out, it would get pretty foggy and steamy inside the ISS. So, so it meets up with the distillate from the urine processor, meets up with the condensation from the heat exchangers from the air conditioner. That goes through a filtration system and ion exchange resins, where they filter out all the non-water stuff. Yep. Still can get through that is microbial things that may have been in there, organic kind of materials. So it goes into a catalytic reactor, which has a catalyst in there and reacts with oxygen, and that basically it breaks down the organic compounds that may still be in the water. That goes through a gas separator, pulls those gaseous compounds out because they've been broken down, and then the now pure water comes out of that. Yep. Goes through another ion resin where it adds iodine in. So it's those ion exchange resins, they exchange ions. So when there's not ions there, it puts ones in, it takes other ones out if they're there. So it adds iodine. Then it goes into a storage system that then goes out to the potable bus. So potable water, drinkable water, has iodine in it. Before the crew actually drinks it, because some crew may be susceptible to iodine. Not all, and it's generally a safe chemical. The Boy Scouts, for example, you bring a little iodine packet to purify your water, right? But we take the iodine out so that it doesn't build up in the crew. At the potable water dispenser where they drink it, or it goes to the oxygen generator.
Okay, and that's our third part.
That's our third. That's our third part. Yep. So the oxygen generation assembly, that is basically as an ion exchange, so it takes the iodine back out. So now it's just pure water again, going into a cell stack, where water is hydrogen and oxygen, H2O. Separates you electrolyze it, and you separate the bonds between the oxygen and hydrogen. The hydrogen gets separated off, and the oxygen goes out for the crew to breathe. Yeah. And then the hydrogen then goes and mixes with carbon dioxide that comes from our carbon dioxide removal assembly, not part of regen, but attached, associated. The carbon dioxide mixes in the Sabatier does a chemical reaction there with the hydrogen, and the output of that is water and methane. Then the methane we vent overboard. Yep. We don't have a use for that. And then the water now goes back into the condensation bus. It basically goes back to the beginning of the system and goes back into the end of the system.
So we just have this kind of constant loop going and feeding.
Constant loop.
And feeding.
Yep. So the crew drinks the water, goes back into their system at the potable water dispenser. And they breathe the oxygen back in, so that comes back in, comes back out as CO2. That goes around and around. The water goes around and around.
All right.
Yesterday's coffee becomes today's coffee.
Yeah. So, I mean, just listening to that, there's a ton of stuff happening in these systems, and it's been running for 7 years now. This isn't something that's been running, nonstop without any issues. It's almost like
that's true.
Plumbing in any house, apartment complex, anything. Issues happen. Right. But that's almost important for us because we needed to learn how to fix those issues, right?
That's right. So a big part of, and this is going to get to one of your later questions that I already know is coming, is developing the technology for future use, right? We hadn't had a regenerative system on space station before. It's a one-off system, so it's not like your car that you have here on the ground or something like that, where they've built thousands of them, and they've been building thousands of them for many, many years. Those still break down, and we still have to fix them. We just take that for rote. Well, on board, we got this large system that's the only one and we're using it as it goes, and we're learning about it as it goes. Some things that we didn't know were going to happen, or that we didn't fully understand about, some tweaks and things like that, where it operates a little differently on orbit than it did here on the ground, that kind of stuff. One of the major things that we needed to overcome early was the crew members. And this goes into the science, and part of the reason where you were talking earlier about we have a crew member on board for 1 year. One of the things that they try to learn is what it does to your body. Now, one of the things that happens is because you're not putting stresses on your bones, your body isn't constantly replenishing or replacing the minor little stress fractures in your bones, and is constantly regenerating your bone. On orbit, you don't have all those stresses, so kind of like muscles can atrophy if you're not using them. You're not using your bones; they can atrophy too. So the calcium leaches out of your bones. Well, when they were doing all the testing here on the ground, it was with people who walk around in gravity all the time.
Didn't have that problem.
Right? Didn't have that problem, and we didn't fully understand how much calcium was really coming out of the crew. We found out very early on with the distillation assembly, where it concentrates the urine. Right, the pre-treated urine. The pre-treat is, amongst other chemicals, has sulfuric acid in it, and it's very acidic, or pH about 2. Right, it's very acidic stuff. Well, the sulfuric acid, the sulfur ions in the sulfuric acid were reacting with the calcium ions from the crew and making basically gypsum, calcium sulfide, which is not soluble, and it clogged up the system. It clogged up the distillation assembly, and gypsum is drywall. It's the stuff inside drywall. So imagine crumbling a bunch of that up and putting inside of a complex machinery. So that's something that we learned, and we reduced our concentration level from that. We stopped before it got that much water taken out, so it was still soluble at that point. And then inside, what we're working on right now should be instituting this coming increment is an alternate pretreat. So we learned from this, and we are changing our pretreat to a different chemical. I think it's phosphorus-based, but and then it stays in solution when it reacts with the calcium.
Okay, so I mean, we have this complex system. It's been running for 7 years now, and before we go, I want to get into why is something like this going to be important for a future mission to Mars? Why is something like this so vital? And also, not just Mars. Has this been? I mean, this is a very complex technology, and you mentioned a lot of things down here on the ground that it's similar to. Have there been any kind of feedbacks, any benefits received down here on Earth from the work we've been doing up in space?
A little bit. For the most part, it's standard technologies or old technology, distilling. For example, that's been going on for eons now, right? And a lot of moonshine stills out in the backwoods of the Smoky Mountains.
This one's just water, though.
This one's just water. So that's it's not a new technological development. It was a difficult challenge getting that to work in zero gravity. So applying zero gravity kind of solutions and developments like that to the ground it doesn't translate as well the other direction sometimes.
But what about trip to Mars? Why is this going to be so vital?
Well, to finish your other question real quick, I'm sorry, is that one of the things that we have used, though, is the microbial check valve. It's one of those ions that ion exchange resins, and it lets the water go through, but because it's a microbial barrier, keeps the microbes from going through. That's actually being used in third world countries, disaster relief efforts, that kind of thing. There's a nonprofit company called Care for Kids, or Concern for Kids, excuse me, that does that. So they are using some of our technology here on the ground. But most of it, the oxygen generator that's used in submarines, that kind of thing. Important for going to Mars, and part of why it was important for us to install here, is that we go through a lot of water as people. You don't realize that you're thirsty, you just get a drink, but we can go through up to 1 liter of water a day. And so, not always. Some people are different, but we'd go through an awful lot of water. Water's heavy, and getting things to space, you pay by the pound. So it's expensive to pay for things by the pound, and it's expensive to get all that water up there. When you're supporting a lot of crew, that's
Yep.
And that's mass that you could be using for bringing up hardware.
Yep. More science, more food,
science,
more anything
exactly.
else. Yep.
So conserving as much water as possible is very important. So and we conserve most of it. Right now we're recovering about 75% of the water from the urine and the condensate.
Mm-hmm.
Hopefully in the future with this new pre-treat we can go much higher than that. So going to Mars, you won't be able to send them water all the time.
Yeah.
You won't be able to.
No resupply flights.
No, right. Or very few.
Yep.
And so you don't want to use all that space for water when you could recover it. So that's why that's been very important.
Well, again, space station regenerative eclipse, the life support, the water recycling, everything turning 7 this week. Very exciting. I mean, 7 years down, and I'm sure there's going to be a lot of advancements in the future as we continue to get ready for the journey to Mars. A lot more work to be done. Again, Dave Mathers, one of our ISS MER managers here for Mission Control. Thanks so much for joining me today, giving us a real in-depth look at everything that's going on that. I really appreciate it, and thanks again for coming in.
You're welcome. Thank you.